Hello, everyone. I'm Santi Adwani from RocketML.
Hi, everyone. I'm Sergio Botello, also from RocketML.
Deep learning has become the workhorse to solve several computer vision problems, including image classification, object detection, semantic segmentation, to name a few. And several industries have picked up deep learning as their main workload to solve problems relevant to their industry. And the need to solve bigger problems, that is, build bigger deep learning models on large amounts of data is increasing. And in this tutorial, we'll cover how to use distributed deep learning on HPC servers to solve large problems, that is, train large, big, deep models. And not only just solve them, but solve them in a reasonable amount of time. That is, the time to solution is an important aspect of training these models, and we'll try to cover these two aspects in this tutorial. The prerequisites for this tutorial are as follows. So we expect attendees to know Python, OpenCV to understand the basics of computer vision and image processing, and basics of deep learning, especially convolutional neural networks, how they work, and what is loss function, what is backprop, and different gradient descent methods. And we expect the attendees to also know one of these three deep learning libraries, either TensorFlow or PyTorch or Keras.
Okay, so I'd like to just give a broad overview of the outline of the whole tutorial, what you can expect to see in the next 4 hours. So the tutorial is basically divided in two large parts. And in the first part, we'll discuss deep learning and distributed deep learning in an application agnostic fashion. Santi will first come in and cover the first part. He'll set the level field by going over basic terminology and concepts and whatnot. Then I'll come in and we'll dive into the nuts and bolts of distributed deep learning in particular. And finally, Santi comes back and talks some more about the pitfalls and gotchas of going from serial single process to distributed deep learning, and some of the best practices to avoid these pitfalls and get the most out of distributed deep learning. In the second part, these 8 experts in their respective fields will talk about specific applications of distributed deep learning. First, Bhaskar and Kaushik from Iowa State University will discuss distributed deep learning for image-based plant phenotyping. Then Vishal and Pandu from Shell Corporation will discuss their work on 3D seismic facies classification using also distributed deep learning. Then Aditya and Shaumik, also from ISU, will discuss their work on topology optimization for additively manufactured designs. And finally, Anuj and Arya from ISU will talk about gaining deep insight in driver behavior using naturalistic driving data. So thanks for attending this conference and this tutorial in particular, and enjoy it.
Thank you.
Thank you.
Hello, everyone. I'm Santi Adwani from RocketML, and in this tutorial, we'll cover basic terminology and concepts regarding distributed deep learning on HPC servers for large-scale computer vision applications. The first concept is computational complexity. So we consider deep learning training as a computational problem, and there are two concepts that are important to understand computational complexity. The first one is space complexity, is the amount of memory required to solve a computational problem. This one would directly impact the memory that you have, that you require for a problem, and the memory that you need to use to build your hardware infrastructure. And the time complexity is the amount of computer time it takes to solve a computational problem. So the computer time actually involves the entire life cycle of a given problem. And these two, space and time complexity, are the most important tenets of computational complexity. And these are the ones that you would pay money for, right? So when you rent an instance from cloud, or when you buy a server, you're primarily paying for your RAM and the processor, right? And these two drive your costs, and understanding space and time complexity is extremely important when you're working on any machine learning problem, and in specific, a deep learning problem. So when we talk about deep learning training, let's go through the steps that will impact your space and time complexities. So you start with training data, and here the training data includes both samples and labels. That is, like you have 1 million images of cats and dogs and the labels corresponding to them, or it can be text data, it can be tabular data, it can be time series data. But for the sake of this tutorial, let's consider all these as images because we're going after computer vision applications. So you have a training data, and then you split this training data into smaller mini batches. That is, if you have, say, 100,000 images, you split it up into batches of size, say, 32, 64, 128, whatever fits into your memory. And you take each and every batch, and you take that batch and pass through the network. Here, the network is, say, your ResNet or UNet or one of these network architectures that are popular or something that you have designed yourself. And you take the mini batch, pass it through your network, and there are two aspects of the network that you need to remember. One is the network architecture and the network weights. The weights are the ones that we are trying to compute end of the day after the training is done. So you have your mini batch, you pass it through your network, and you get your loss function. And once you have your loss, you do a backprop to compute your gradients. And once you have your gradient, you basically use that gradient along with a gradient descent method, one of the variations of a method, and you adjust your weights. Once you adjust your weights, you take the next mini batch and pass it through the network, compute loss, and compute the gradient, and compute your step, and update your weights. So when you go through an entire set of data, right, that is, go through all your 100,000 images, and that means several 100 plus, 300 plus mini batches, that is called one epoch. Okay. So a space complexity in this case is the amount of memory required to store the mini batch, which is nothing but, say, 32 times an image size or 64 times the given single image. Your model weights, that is the weights that determine the network and maps from the network architecture to the floating point values which for the tensors. The intermediate tensors, that is, when you do some matrix vector operations, you need to create some intermediate tensors to keep track of the transitions between the layers, right? So you need to save them in memory. So the intermediate tensors also occupy memory, and optimization tensors, right? So once you compute your gradient, before you adjust your weights, you need to do some calculations over gradients. Either you have to pick the previous gradient or some function of some gradient history, or you're just using the gradient as it is. But there are still some tensors you need for optimization's sake. And all these would require memory, right? And that constitutes your space complexity of this problem. When it comes to time complexity, it is the amount of time required for forward propagation. That is basically take the data and pass it through the network. Back propagation, that is, once you have the loss, computing the gradient and adjusting the weights, right? So that is taking the step. So these space and time complexity, that is in terms of memory and time, drive your computational needs and also time to solution. Okay. So this is a key concept that we'll continue to use for most of the presentations today, and I'd like to pay attention to this piece. So when it comes to the compute infrastructure, right, we start with a single node. Single node constitutes of primarily these three components: the disk, that is the hard disk, SSDs or flash drives, where you have your tens of gigabytes of data, and then you have your RAM, which is basically your it's called DRAM or host RAM, or like sometimes just RAM. it's the amount of memory that you have on your machine, right? And that is for small, from your laptops, it can be 8 gigs, 16 gigs, and 32 gigs, and so on. And on cloud, you can rent a virtual machine with 300 plus gigabytes of memory, and in some cases terabytes of memory, right? So that is your RAM, and then a CPU, right? It's an Intel CPU, AMD CPU, or RAM CPU. So these disk, RAM, and CPU constitute a single node. Right? This is a basic unit of our operations. And in the context of deep learning, the mini batch, the model weights, and the optimization tensors are the ones stored in the RAM. And the forward propagation, the backprop optimization updates are all done on the CPU. Okay, that's where different hardware components are used. So when it comes to time to solution, right, that is how, like when you start Go and getting to a solution, the time to solution is a combination of time for data movement, that is, you're moving data between the disk and the RAM, which is nothing but I/O time, and time for computations, right? That is, how much time does it take for forward, backward prop, and backprop and optimization constitutes your time to solution. Okay, so single node is a disk, RAM, and a CPU, and these are the space and time complexity impacts on the hardware. So the next level in hardware is single node with one GPU. So when we're talking about single node with one GPU, you have the GPU, which constitutes GPU memory and GPU cores, right? So it has its own memory. And in this case, the mini batch, model weights, and optimization tensors are generally stored in GPU memory. And GPU memory is, in general, and majority of the cases, right, it's far less than the amount of host RAM or RAM that you can get on a single machine. So GPU memory, that's another component we added in this hardware configuration. And then the forward prop, back prop, and optimization updates are now done on a GPU. So GPUs make computations way faster, right? It's a known fact. It's 10 plus times faster than CPUs for some of these workloads. But there is a data movement overhead, right? That is, the data now has to go all the way to GPU memory, and it adds an overhead of data movement between RAM and GPU memory, and that adds to the time to solution. Okay, and that's something you want to keep in mind, because end of the day, the time to solution is what we are trying to, one of the things that we are trying to optimize for. So now the next level is single node with multiple GPUs. Okay, so DGX 1 or 2 is a classic example of a single node with multiple GPUs. That is, in that case, you have a disk, you have RAM, and then you have multiple GPUs, each of them with its own GPU memory and a CPU, and the GPUs are connected together with NVLink, right? So NVLink is a new hardware component. It basically connects all these GPUs for inter-GPU communication. Okay, so same as before, the mini batch, model weights, tensors are stored in GPU memory. Forward prop, back prop, optimization operations are done on GPU, and there is a data movement time, so additional overhead here. That is, the data has to sometimes move from GPU to GPU. Okay, so we have more GPU memory footprint because you have more GPUs, and it's a multiple of number of GPUs times GPU memory, but adds inter-GPU communication overhead when you're trying to solve these problems. Okay, so single node with multiple GPUs is the next hardware configuration that is important to know. Now we're jumping into HPC. So multi-node HPC cluster, right? So that is, now we are no longer talking about just a single node, that is single disk, RAM, CPU combination. We have a collection of nodes, and this collection of nodes, along with a parallel file system, This is a parallel file system that all these individual single nodes can access data from. And you have a communication network layer, which is basically connecting all these different nodes with either with Ethernet or an InfiniBand switch. All together, this constitutes a high-performance computing cluster, right? So you have some powerful CPUs connected together with a parallel file system where all of them can access data from, and you have a network switch that is connecting all of them for inter-node communication. So this we call a multi-node HPC cluster. And as you can see, once you have more of these nodes, there is data movement, not just from disk to RAM and to RAM to CPU. You also need to move data between the nodes, right? That is the inter-node communication overhead. And so there is more memory footprint because you have more machines, but you also have to consider the communication overheads when you are trying to solve problems on a HPC cluster. So now we have multi-node single GPU HPC cluster. That is, each node has one GPU, and you can club all these together, and you still have a parallel file system. You have an Ethernet, InfiniBand, sometimes NVLink between the nodes, and that constitutes a multi-node single GPU HPC cluster. So there is more memory footprint, GPU memory footprint specific, but adds communication overhead, right? So in this case, the communication overhead could be from going from GPU memory to RAM and then connecting all the nodes and communicate, and again, RAM to GPU memory. So there are more overheads that needs to be taken into account when you're working with multi-node single GPU HPC cluster. And the last and the final configuration is a multi-node, multi-GPU HPC cluster. So in this case, a single node will have more than one GPU, that is more GPU memory per node. And you have a parallel file system, a network layer, either Ethernet, InfiniBand, or NVLink. And this constitutes the most powerful HPC clusters, right? That is multi-node, multi-GPU HPC clusters. And when you group all of them together, you have very large GPU memory footprint, large CPU memory footprint, and quite a bit of degrees of freedom to optimize and solve large problems. Okay. So more footprint, but adds communication overhead. So for this tutorial, we are not going to deal with the single node or single node with one GPU. Most of our focus would be when you have more than one GPU, and in specific, a single node with multiple GPUs, multiple nodes with single GPU, and multiple nodes with multiple GPUs. And the last case, multiple nodes with CPUs, right? The reason multiple nodes with CPUs or multiple nodes HPC cluster is important because sometimes even to narrow down a problem and fit into one GPU memory, it can be expensive, or you may not be able to fit a problem in a single GPU memory. So in that case, an alternative is to just use multi-nodes with CPUs. So how to get access to these clusters, right? So, well, good, you have these different configurations. How do you get access to these? So there are different ways to get access depending on where you are currently doing your data science practice or deep learning practice. If you're in a university, check with your university on if they have university HPC clusters. And some of them do, some of them don't, but they would have some way to get you access to a HPC cluster. If you're working in a national lab, or if you're associated with a national lab, you have HPC clusters managed by national labs, and that would be another place where you can get access to these. In some large organizations, they have in-house HPC clusters. Right? That is, they have built data centers and they have built HPC clusters for internal workloads, and you can check with your IT or your management to get access to them. The last option, which is basically more of a public option, is on-demand HPC clusters on cloud, right? So all these providers, AWS, Azure, Google Cloud, all those guys have some kind of HPC support. and you can get HPC cluster access through one of these cloud providers. And if you have any questions on these, right, how to get access to one, feel free to reach out to us at RocketML, and we can help you get access to one of these or set you up with an on-demand HPC cluster on a public cloud. So with that, conclude this tutorial. The summary is we covered the basics of computational complexity, talked about space and time complexity in the context of deep learning training. And we discussed different CPU and GPU cluster configurations, starting from single node with a GPU, multiple GPUs, and how they are configured. And last, gave a quick summary around how to get access to these HPC clusters for doing your deep learning training workloads. Thank you.
Hi everyone, and welcome to part 2 of this tutorial on distributed deep learning on HPC servers. So on this part of the tutorial, I'm going to be focusing on the nuts and bolts of DDL, and the talk is split into 2 main parts. On the first part, I'm going to motivate the need for distributed code, first in general and then in the context of deep learning specifically. And we'll do this by looking along 3 different axes: the evolution of hardware over the last several decades, then how deep learning evolved in the last several years, and finally looking at the limits when deep learning might break on single machines or small machines, especially in the context of GPUs. And then on the second part, I'm going to do a survey of the existing DDL solutions out there, first taking a look at the landscape of available strategies to parallelize deep learning, what are their pros and cons and so on, and then looking at specific DDL solutions out there, DDL libraries, specifically talking about Horovod, PyTorch, TensorFlow, and finally our own homegrown distributed deep learning solution from RocketML, which is RMLDNN. And for a couple of these, we're going to look at some demos as well. All right, so let's get started. Okay, so I'd like to start by first motivating the need for distributed deep learning. And in fact, first I will take a step back away from deep learning or machine learning even, and just talk about the need for distributed code in general. And one way to answer this question is to look at hardware and how hardware has evolved in the last several decades. And there's this interesting article here, 42 years of microprocessor trend data, that shows this plot, which has some very interesting insights. In particular, we can look at this brown curve going up, which is the transistor count on microchips over the last 4 decades. And one can fit the line here and see that this, up to 2019 and probably until today, satisfies a power law. So Moore's law, which I'm sure you're all familiar with, states that the prediction that the transistor count on microprocessors would double every 2 years roughly is still pretty much holding to this day, right? However, if you look at the clock frequency in the green dots here and the single thread performance in the blue dots, these have not kept up. The clock frequency seems to be stabilizing starting in 2005 or so, and the blue curve hasn't quite stagnated yet, but it's not keeping up with the power law. And the explanation for this is, although we have more transistors, the manufacturing processes used to shrink these feature sizes and transistor sizes has led somehow to a decay in transistor performance in such a way that just putting more transistors is not giving you necessarily more performance or as much performance as you'd expect to keep up with the power law. However, look at the black curve. The number of logical cores in these microchips has been going up at least since 2005, exactly when the clock frequency started to stagnate. And they probably realized that the only way to keep up the performance is to parallelize, to increase the number of cores. And that's why, although it's been true that in the past, if you just swapped your microprocessor with a new one every 2 years, you'd automatically get faster, right? Every application would run faster in your system. That's not true anymore. Single thread applications will not get faster automatically at all. maybe your computer will still get faster, but that's because the OS leverages these extra cores and parallelizes code for you. But your single thread code won't run any faster automatically with new chips. You'd have to take advantage of the multi-core and write parallel code for that. So that's one good motivation for parallel code in general. If we now look at the specific case of deep learning, so here I'm showing a plot from an OpenAI article, and there's lots of interesting studies that these folks do on the history of deep learning and current trends and future outlooks. And one of them shows this interesting plot where they plot the compute effort or compute power necessary to train different models, deep learning models that have come out in the last several years. So on the y-axis you have petaflops per second day, which is just flops. You can do the math, and this is 10 to the 20 flops. So a value of 1 here means 10 to the 20 flops. On the y-axis, on the x-axis, just the years. And they show the compute power to train each one of these deep learning models. And as you can see, there is a power law going on here. If you fit the line, you see, though, that this power law has a factor of 10 every year. So at every year, the compute power needed to train these models grows by a factor of 10, while Moore's law, in blue down here, grows by a factor of 1.4 roughly each year. So there's a growing gap that's showing no sign of decreasing. It's just increasing between the needed compute capacity to train new deep learning models and the hardware acceleration provided by Moore's law. It's worth mentioning that hardware accelerators, like things like GPUs and FPGAs and AI-specific chips, these have helped quite a bit in bridging that gap somewhat, but a big gap still remains. I mean, they're not enough to keep up with the hunger for compute power from these deep learning models. This is from another. This plot is from another OpenAI article, where they take a look at the question here that they analyze is, what are the most important ingredients or components during training that affect model performance, measured, say, in terms of quality of the model in doing predictions? And what they, after training several different types of neural language models and compare the results, they realize that things like network architecture and optimization parameters and batch size, these things matter much less than these 3 critical factors that contribute the most to model performance. And these are the number of model parameters, just the size of your network, the data set size, how many samples you use for training, and the amount of compute. And that this last one is, in fact, how long you train for, how many epochs do you train for, or how many machines you throw in your parallel deep learning training. And what they show, they collapse lots of these experiments into single plots and show that model quality, as measured by the test loss, has a power law dependency on each one of these factors, right, separately, as shown here. And here I show specific examples of those power law dependencies for 3 different models, keeping or varying one of those factors and keeping the other 2 constant. For example, on the upper left here, I show the accuracy from models trained with the ImageNet dataset. And in fact, this is the top 5% accuracy for different models trained on ImageNet as a function of the compute capacity or compute effort needed. And as you can see, for all models, it is true that the accuracy of the model improves as more compute power is put into training. Some models improve better than others or increase faster than others, but the story is the same for all of them. On the right-hand side, this is a result for accuracy on ImageNet training, top 1% accuracy on a self-supervised model and at fixed compute power. So this is fixing the other 2 factors and changing the number of parameters in the network. And the same story repeats. You also have a power law going on here of model improvement with network size. And last, in the bottom, results for mean average precision, the MAP, for training an object detection model on the COCO dataset at fixed compute power and fixed network size, right? And just changing the data set size used. And again, there's a power law dependency. So these are three independent, completely different models being trained and showing those power law dependencies that we mentioned. And the black and red line in these plots are just two different data augmentation strategies that the author used, but the message is the same, the results are the same. Now, one last thing about this topic of why use distributed deep learning. One typical use case is like the ones we've seen before. You have a model to train and you can throw in more nodes, more compute capacity, and each one of these nodes will take a small chunk of the problem, a smaller chunk of the problem, and therefore solve it faster. And by this, you can scale out. You can get faster by scaling out your solution. In many cases, however, like memory-bound problems, you can't even fit a problem on one machine, right? Especially if you're dealing with GPUs that notoriously have smaller memories than CPUs. Sometimes you cannot even run one training on one sample. Say you cannot fit one sample in memory. And here your options are either to scale up, get a bigger GPU, a GPU with more memory, or scale out, split your problems into multiple GPUs. Just an example of that situation. Here I show results from our experiments where we trained a 3D UNet network. And I show the peak memory during training as a function of the size of the samples used, the size of the images. And as one can see, just going from 64 cubed to 128 cubed, we in fact surpassed the memory capacity of the RTX 6000, Tesla RTX 6000 GPU, which has 24 gigabytes of memory. And by doubling the size of the image, once more, the linear size of the image, going from 128 cubed to 256 cubed, both the Tesla V100 at 32 gigabytes and the Tesla A100 at 40 gigabytes, neither of them are capable of solving this problem because we need now about 250 gigabytes of memory. So in order to tackle this, we had to go to a cluster of CPUs, and we use this one in particular with 256 gigabytes per node, which just shows that this is one more motivation for distributed deep learning, that in memory-bound problems, where you cannot even have difficulty fitting one training sample into the GPU memory, you have to either scale up or scale out and parallelize. So now that we have looked at the motivations to use distributed deep learning, I'd like to take a look at the available solutions out there to distribute deep learning model training. In particular, I'm going to look at several open source DDL solutions out there, and at the end compare with our own homegrown RocketML solution for the same problem and see how they compare. And first of all, it's important to say that not all of these libraries sit at the same footing, meaning they're not all full-fledged machine learning libraries or deep learning libraries. For example, PyTorch and TensorFlow are pretty full-fledged deep learning tools. You can use them for anything, training models, running inference. They have their own distribution, built-in distribution facilities to run in parallel and so on. However, things like Lightning and Deep Speed, they're like enhancers. They sit on top of PyTorch, these two, and they enhance the PyTorch experience. They might add functionality. They might make the API simpler or make some tasks easier and whatnot, but they are not full-fledged deep learning libraries in their own right. Same for Keras. Keras used to be a very powerful API that used backends, PyTorch, TensorFlow as backends. Recently, it became actually integrated into TensorFlow. As of TensorFlow 2.0, it became their de facto API of sorts. But also, Keras is not a standalone machine learning or deep learning library. MXNet is a full-fledged deep learning library, but it doesn't have out-of-the-box support for distribution and parallelization. And you'd have to use something like Horovod, which again is not a full-fledged library. It is a distribution engine or layer that you can put on top of PyTorch, TensorFlow, MXNet to run in parallel. So obviously each one have their own uses and applications and pros and cons, and we'll take a look at each one of these in a little bit later. And also they might require different degrees of user intervention and expertise, how much code you have to write to go from single to multi-process, how much do you have to know about HPC, launching jobs, managing different workers, ranks, and so on, data distribution. So we'll also take a look at these. But before we go there, I'd like to set the stage by talking about what are the main steps that each one of these libraries have to perform in order to support distributed deep learning. And taking even one step further back, what is it that even a serial single process machine deep learning training activity involves, right? What are the steps to train a model, say, even on one process? And that's what's shown in this diagram down here. So the process mainly consists of these steps, no matter how you do each one of them, which is you start with some data, training data, and some network, right? And so the first step is to split this data into mini batches. And I'm assuming you're training on one processor, one machine, say. Once you split this data into mini batches, you forward each one of these mini batches through the network. So you apply each one of the layers, operates on the mini batch. And at the end, you compute some kind of error or loss, which is the difference between what the network produced and what you expected it via given by your target data. And then this loss now can be used to run backpropagation, which is pretty much backtracking that loss to compute the error, the adjustment that each parameter of the network will need to have, right? And this vector of all the parameters adjustments is called the gradient, right? Finally, you take this gradient and you use an optimizer to adjust the weights of the network given the gradient. And there's many algorithms to perform this process. Given a gradient, apply the corrections. And then the process goes on again for the next mini batch. And when all the mini batches are done, that's the end of the epoch. And you can now run a second epoch until convergence, say until your loss value is small enough or something like that. Now, like I said, no matter how the distribution process works, how the library distributes this training process, they have to accommodate all of these steps. So they have to be able to split the data, not only among in mini batches, but among the workers that now participate in training. They have to somehow take care of forward and back propagation. These processes can be done independently by each one of the workers or split across workers depending on the parallelization strategy. And at the end, they have to be able to combine these gradients somehow, right? If each one of the workers computes its own gradients, say, in one of the strategies, you have to be able to average these so that everyone can update their weights with the same gradient, for example, right? So these are the basic 4 steps that they all have to do, but how they do it is up for grabs. And there are different strategies to perform each one of these, and that's what we're going to take a look now. So the main different strategies out there to perform distributed deep learning can be bundled into 2 main independent axes, right? And these would be the partitioning strategy, which is how to split the data or the layer implementations and the operations among the available workers. And there are 3 main ways to do that, which are the data parallel strategy, model parallelism, and pipelining. And we're going to take a look at each one of them next. And there's a second axis of independent choices here, which is the synchronization strategy. And that's how and how frequently parameter updates are communicated among the workers doing the job. Technically, this can be split into 2 further independent axes, so a total of 3. And these would be the axis of model consistency. So how and whether local parameters are always kept in sync, consistent among the workers, or if they can be allowed to go stale. Like if one worker can be working on slightly stale old data compared to the others. And the third axis would be the parameter distribution or centralization strategy, whether the parameters are all communicated among the workers So that would be a decentralized solution, or communicated to a server, some sort of server that receives and sends these parameter updates, and that would be a centralized solution. So I'm going to be making the simplifying assumption that consistent schemes are always implemented decentralized, right? So if the workers are always kept in sync, that's consistent. They always communicate among themselves. And on the other hand, inconsistent schemes are always implemented centralized. So the first type of distribution strategy, and probably the most popular, the most widely used, is the so-called data parallel strategy, in which the data itself is partitioned evenly across the workers, right? And the model, the network, is actually duplicated, not split, but duplicated among all the workers, right? So each worker operates sort of independently. They do the forward and backward propagation steps independently on their chunk of the data. And the main advantages of this strategy is that it's relatively easy to implement. You don't have to do much about the forward and back propagation passes. You just take care of the data splitting and the gradient communication at the end. And for that reason, it allows for best strong scaling. So you can get the best scaling out of this scheme because the amount of communication will be limited, right? So you do a lot of work before you have to communicate the results. The main drawback of this strategy is that it puts a limit on the size of the model, the network that you can use. And this is simply because the networks are duplicated among all the workers. So if it's big enough that it can't fit on a single worker, then adding more workers won't help because you have to duplicate it. Right? So that's for very large networks and models, data parallelism might not be appropriate. The second strategy is the so-called model parallelism. And here it's quite the opposite. The data passed through the network for each one of the workers is the same, but the layers themselves are distributed. They're split among the workers so that when data passes in and say a convolution layer operates on that piece of data, the convolution operation itself is performed distributed, right, across multiple workers. The main advantage of this, of course, it allows bigger models now. So it mitigates that issue or solves that issue with the model parallelism. That is, there's a limit on the size of the model that you can use. Here, because the model is split, the layers are split, if they're big, just add more workers and you'll be good. And it doesn't give you strong scaling necessarily, but gives you the best weak scaling. So the ability to run larger and larger models. The cons of this strategy is obviously it's much harder to implement. You have to implement the operations themselves distributed and all the communication between the workers. And this layer interdependency adds substantial communication overhead. So now instead of say running convolutions independently, they have to run them in parallel. And for example, fully connected and conv layers will need all-to-all communication. It's like implementing a matrix multiplication in parallel, right? There's a lot of communication involved. And finally, pipelining, which sometimes people confuse with model parallelism, but they're not the same, is when you don't split the layer, but you take the entire layer and you put on one rank. Then you take the next layer of the network and you put in another rank. So each rank is responsible not for a chunk of the data, not for part of the operation, but for a whole operation and only that. Right? That's what pipelining is. You can see in this cartoon here. The main advantage, or some of the advantages, are it also allows for bigger models compared to data parallelism, and it has a fewer communication points compared to model parallelism, and it's also slightly easier to implement than model parallelism, although it's not trivial. It's difficult. The cons it's difficult to implement compared to data parallelism, of course. But the main disadvantage of this scheme is that it's hard to achieve good load balancing. As you'd expect, if one layer is much heavier than the next, this worker here will be a bottleneck, right? The data will spend much more time on worker A before going to B, simply because this layer is harder to process. And in particular, complex networks, for example, with skip connections, are particularly challenging because of this load balance issue. Now to the next axis that I mentioned. Implementations can differ in terms of their communication strategy. In synchronous communication strategy, all the available workers train the local mini batches in lockstep, meaning they have to finish their mini batch and communicate their gradients at the same time before they can go on to the next mini batch. And by doing this, by taking this gradient all at the same time and updating their weights before going to the next mini batch, they always operate on the same replica of the model. The models across workers are always in sync, right? So gradients are synchronized after a mini batch, and this is usually done with some sort of collective communication like an all reduce, and the ring all reduce is the most popular implementation because it's efficient. So it's pretty much all the nodes communicating among themselves at the same time at the end of each mini batch. And in opposition to that, there's the asynchronous communication paradigm, where the gradients are not communicated at the same time. So weights are allowed to go stale on some workers. So some workers might be working with a slightly different version of the model as the next worker, and that's okay. That's allowed to happen. And by doing this, each worker consumes the next available piece of data as they finish the previous, right? So they don't have to wait for each other to start on the next piece of data. This is typically implemented in what's called a parameter server infrastructure. Typically, not always. There's exceptions here, but typically this is done by assigning some workers in your cluster to be servers. So they don't participate in training. They just serve as parameter servers. They fetch, they're provided parameter updates from the ranks, and they update ranks when they need with new gradients. So these are the two communication styles, synchronous and asynchronous. And that concludes this module on the different types of distributed deep learning libraries and their parallelization strategies. In the next module, we're going to look at more specifics of those libraries that I mentioned before, and what their pros and cons, and how they can be used, and what they provide. So the first distributed deep learning library that we're going to take a look at is Horovod. And Horovod is an add-on, is a distribution layer added on top of the most popular backends like PyTorch, Keras, and MXNet. And it's developed by Uber. And the goal that they state in their documentation is to require minimum added code and maximize speed up. So we'll take a look at how they do that. And it's modeled after the synchronous data parallel paradigm. So they use data parallelization and the synchronous mode of communication, mainly using MPI for inner CPU communication and NCCL as the backend for GPU communication. Pipelining can be implemented, but it's delegated to the backend, meaning you have to use, say, TensorFlow or PyTorch's API to assign individual layers to individual GPUs. For example, like this in TensorFlow, you would say you put this with TensorFlow device scope statement before some layer and assign it to GPU number n, right? Horovod itself doesn't directly support pipelining. It delegates that support to the backend. Here's some code snippets showing in bold red the statements that you have to add to a serial code to turn into a distributed code using Horovod. And as you can see, it's pretty thin. It's not a whole lot of code. You have to initialize Horovod here, as done here. You have to then scale. They recommend that you scale the learning rate of the optimizer with the size of the cluster, the number of workers in the cluster. And this is to compensate for the increased batch size. So apparently they scale the global batch size internally, and to compensate for that increase, they recommend that you increase the learning rate by the same factor. Then you have to wrap your optimizer, in this case it's an Adegrad optimizer, within their distributed optimizer class, and use this guy from now on. And finally, add this hook to broadcast variables from rank 0 to the remaining ranks during initialization. And that's all. From that point on, this script will run in parallel with Horovod. And how do you launch the job? They offer two ways of doing. They have this wrapper application called Horovod Run, to which you can pass the number of processes. I want to run in 8 processes, say, using these 2 servers. You pass the host names of the servers and the number of processes on each server. And that's it, and then the name of your script. Or you can directly engage MPI Run, which is the launcher engine of MPI. There's more parameters, it's more verbose in this case. All these MPI parameters are apparently encapsulated here in Horovod Run. But either case, pretty simple to run once you have a cluster up of machines. Finally, let's discuss their performance. They have this flagship scaling results here on their website, which shows the image per second. So that's the throughput during training to train different models, 3 different models, as a function of the number of GPUs used, right, from 1 to 512. So this looks pretty good. It's pretty impressive. I just wanted to make 2 comments, 2 caveats here about these results. First, they claim that this is used synthetic data, which means data is generated from I instead of read from disk, which helps with scaling because you take I/O out of the picture. So that's good for scaling, but it might not be very realistic. In a realistic scenario, you actually read from disk and you have the overhead of I/O, which will hinder your scaling, your speed up a little bit. So that's kind of an optimal scenario. And second, and most importantly maybe, they say before that you have to scale the learning rate of the optimizer to compensate for a batch size increase, which means that behind the scenes they are scaling the global batch size with the number of workers, which helps scaling as well, which helps the speed up, because the more work each worker has to do in between communication cycles, the better for scaling. But that might hinder convergence. SGD-based training of neural networks works best with smaller batch sizes. If you increase the global batch size by keeping the local batch size fixed, you might hurt your convergence. And we're going to talk about this interplay between batch size and cluster size later in the talk. But here I just wanted to point out that these 2 factors might be making this scaling result a little artificial, and in a real scenario, it wouldn't be that good. So to wrap it up, that's all I wanted to say about Horovod. It is a very powerful distribution engine that runs on top of the most popular backends. It is very easy to use, and it does require a low coding hurdle to turn a serial script into a parallel script, and it has potential for good scaling with the 2 caveats I mentioned before. The 2 cons that I could point out, it wasn't that easy to install for me. I struggled a little bit installing this thing. Maybe some people have better experiences. And they do mention in the documentation that you need to install MPI and NCCL yourself. And that might be a hassle, as they say, hopefully done only once, but it's not done automatically for you. And maybe the main disadvantage is that it doesn't have any kind of facilities to handle data splitting among the workers. That's something that's delegated to the user. You have to take care of assigning different data to different workers. What they do is simply to allow different workers to fetch data from the global data set randomly. And that might not be good because there might be a lot of overlap between data being processed by these workers. So you have to implement something yourself. But in any way, there's a lot of sample code available. Horovod is used by lots of folks. You can take a look here, and lots of good documentation also explaining how to install, how to use, etc. So the next distributed deep learning library that we're going to take a look at is PyTorch. And PyTorch is a fully self-contained deep learning tool which has its own distribution, built-in distribution facilities. And it's modeled after the synchronous data parallel paradigm, and it uses by default the library GLUE for inner CPU communication, although MPI can be used. However, GLUE is installed by default, and MPI has to be installed by the user. And for GPU communications, they use NCCL. Although data parallel is the default, pipeline parallelism can be implemented, but it is, like in the TensorFlow case we showed before, it is the responsibility of the user to assign specific layers to specific CUDA devices by calling the .to function to pass this module into that GPU, and that has to be done for tensors as well as dealing with load balancing challenges in pipeline implementation. That's all the responsibility of the user. And PyTorch also even offers this distributed RPC library, which is a lower level library of remote procedure call primitives that would allow one to have even lower level access to the communication among the workers and implement more complicated solutions like centralized architectures, parameter servers, and so on. So here, a quick overview of the evolution of DDP support in PyTorch. The simplest way to get it done is using this data parallel package, which supports single node multi-GPU parallelization. So it's very easy to use. It's a one-liner to turn your script from serial to parallel, but it only supports running on one machine with multiple GPUs. It has also limited scalability due to the fact that the module is replicated on each device at each forward pass. And because it's a multi-thread implementation in Python, it suffers from GIL contention across these model replicas. The next step in the evolution is this distributed data parallel package. And this is truly multi-node, multi-process, and it allows you to run on multiple machines, each one with multiple GPUs. It has better performance also because the model is broadcast only once, as opposed to after each forward pass. It's only broadcast during DDP construction, during the object construction. And like I said, it supports truly multi-process parallelism, no GIL contention. It's slightly more complicated to use, but that's by a tiny amount. And it's really the recommended way to go, either if you're using multi-machines with multi-GPUs, or even in the case of single machine multi-GPUs, that's the preferred way to go. And the last package that they offer is this distributed RPC, like I mentioned before. That's a lower level package for remote procedure call primitives, and it can be used to implement more sophisticated solutions, but it's much more complicated to use. So here's a code snippet showing what you have to do to turn a serial script into a parallel script using the distributed data parallel package of PyTorch. And it's pretty much 2 lines. And we'll see a demo later where I actually use these, and there's one extra line that we have to use, but it's pretty simple. The first thing that has to happen, you have to initialize the process group by calling this function on the torch distributed class and passing the communication backend that you want to use, say glue, and optionally passing the rank and the world size. These can be inferred automatically, as we'll see. And the last thing is just wrap your model. My model here is a simple single layer network. But anyway, just wrap this model inside the distributed data parallel class, passing also the device IDs. And this is the list of devices that you want to bind this process to. Typically, we bind one process to one GPU on the machine, so this list will be a single number. And that's it. That's all it takes to use the distributed data parallel package. Now, just a quick overview of the design of the implementation of DDP in PyTorch. On top, we have the distributed.python file, and that's where this is the entry point into the DDP implementation. It implements the initialization steps, the construction of the object, and the override of the forward function for the NL and then parallel distributed data parallel module, which calls into the C++ libraries underneath. It's also responsible for broadcasting the model buffers from rank 0 to all the other processes. Down on the stack, we have this reducer, which is the module that provides the core implementation of the gradient synchronization in the backward pass. So that's responsible for synchronizing the gradients after all the ranks are done with the backward and forward pass. And sitting at the bottom, we have the lower level communication libraries like NCCL, GLUE, MPI. So the interface into these libraries, supporting things like collective communication primitives, broadcast, all reduce, and so on for inter-node communication. So one nice feature that, nice facility that PyTorch has is this distributed sampler class under the utils data distributed package. And what this does, it helps the user with the splitting of the data among ranks, among nodes. And this is what I said, that Horovod, for instance, doesn't provide something like this. So by creating a sampler of this type and passing it into the data loader, we transform our data loader from serial to distributed. So it takes care of splitting the data across the workers, taking care of remainders, and making sure there's no data overlap, and so on. So it's pretty easy to use. To launch PyTorch in distributed mode, we have two options. If you're running on a single node multi-process, or say multi-GPUs on one node, all you have to do is to pass this -m torch distributed launch and the number of processes per node, and that's it. The rest is your script and your arguments. If you're running multi-node, you have to launch it with more parameters, and I don't want to spend too much time here now because I'm going to show how to use this in the demo coming after. And so that's it. Just to summarize, PyTorch is also a very easy to use library for deep learning with built-in DDL support. It also has a distributed data sampler that is provided and can be easily used to split the data. The only con I can see, it has no out-of-the-box support for synchronous paradigms like parameter servers, but that's really minor. One usually doesn't need that. The solution that it has is pretty sufficient. It is highly documented, and there's lots of examples, tutorials, classes out there. I didn't even scratch the surface of what PyTorch does. And here are some examples of places you can find good tutorials and good sample code. Okay, now I'd like to show a demo in which we'll use PyTorch to run distributed deep learning. And for that, I have here a machine with 2 GPUs, and we're going to use this script, which is pretty standard PyTorch code, to train a simple model on the MNIST dataset. And I'd like to focus on the parts of the script that have to change, what you have to add it to make it distributed. But let me just go over the whole thing real quick. First here, there's this class inheriting from the NN module, PyTorch class, which is a standard definition of a neural network, a small network and its layers. Skip this. Some argument parsing. And then here, the first line that is different. We need to initialize the process group using the torch distributed library and passing the backend. Since we'll be training on GPUs, we use the NCCL backend. This is standard initializing the MNIST dataset, loading the MNIST dataset, and defining some transforms on it. Here, we use the same data loader to load data into the network that we would use on a serial run, but we use a sampler. We pass a sampler into it, which is this distributed data, a distributed sampler. And what this does is it splits the data and distributes it to the available workers in the cluster, and taking care of things like remainders and avoiding data overlap and all this good stuff. So it takes that burden of data distribution and management from the developer. And I do this for both train and test data loaders. Print some stuff in the beginning of the run, And then here, the last thing you have to do is to wrap your model inside this distributed data parallel class upon construction, and also pass the device IDs. What I want is to bind each process on a machine to a different device, to a different GPU. So I just make this list equal to one device ID, and I get it as the rank of the process modulo device count. So with that, I guarantee that each process on a node has a different device and gets bound to a different CUDA device, a different GPU. And that's it. The rest is pretty standard. There's an optimizer, and in here I loop over the training and test cycles, right? And what these functions are standard serial PyTorch stuff. The train function does a forward pass, computes the loss and the backward propagation and optimizer step. It then prints some progress data and the loss, and the test function pretty much the same, but well, does a forward pass, computes the loss, and computes the accuracy and prints the accuracy down here. All right, that's pretty much it. So first, let me run this serially, just using one GPU to see how long it takes and whatnot. So notice that one process prints this header, and it's using 60,000 samples, which is the entire data set. And there you go. One epoch takes 18.5 seconds, 18.5 seconds to run. Okay, so all that you have to do to run this distributed is to add this -m torch distributed launch parameter in the command line, and how many processes per node. And this usually is the number of GPUs that you have in the machine. So there you go. Now 2 processes are launched and on the same host, and each one takes half, 30,000 training samples out of the total. And we went from 18.5 seconds to 9.3 seconds, almost exactly half the time, which is what you would expect when running on 2 GPUs on the same machine. And notice here, just again, how the 2 processes have different ranks and take half of the data, train on half of the data. Now, this is one machine, 2 GPUs. The last thing I wanted to show is how do we run this on 2 machines, like 4 GPUs, 2 on each machine, right? So the truly distributed deep learning. To do that, I go back here to the master. I have a cluster up with 2 machines. We were just sitting on one of the machines, and I went now to the master, and there's two GPUs machines up. And the only difference that you have to do in order to launch these jobs on different machines is the command line now takes not only the number of processes per node, but also the number of nodes, which will be 2 in our case, and this node rank, which has to be a unique ID different on each node where the processes land, right? And because I cannot set this node on the command line as I launch, I'm going to use Slurm to launch the jobs. So I cannot set different node ranks for different jobs as they land. The solution here I have is to create this tiny simple script, which will then call this thing. And when it lands on the machine, I leverage Slurm node ID, the environment variable Slurm node ID, which will be different on each node to set this node rank. Okay, it's a pretty simple solution. So all I have to do now is use Slurm to launch these. And I expect now to see 4 processes, there we go, on 2 different hosts. And each one taking a quarter of the data, 15,000. And here it took 8 seconds per epoch compared to 9.5 that I had before. It wasn't a big speed up going from 2 to 4 GPUs, but we did run on 4 GPUs. We can see here from the processes and their ranks and whatnot. And the explanation here is simply because this is a very small problem and the batch size is very small, so the communication overhead is too big and it dominates. So scaling out and adding more machines won't help you in such a small problem. But in any case, that's how you run distributed deep learning using PyTorch on both single and multi-node. Let's take a quick look at TensorFlow, which is another fully fledged, self-contained deep learning library, open source library out there. And it also has its own built-in support for distribution. In fact, it's one of the most complete distributed deep learning solutions out there. It not only supports single node and multi-node parallelization, but also has out-of-the-box support for asynchronous parameter server strategies. It has had support for a while for TPUs, tensor processing units, and as of TensorFlow 2.0, it has incorporated Keras as one of its supported APIs, thus combining the power and the broad functionality of TensorFlow with the expressivity of the Keras API. We don't need to look in much detail at these strategies because these are similar to what PyTorch does, and we covered that already. And we also covered it in the broad sense of distributed deep learning strategies. But just to tie it up quickly with TensorFlow, it offers this TF distributed mirrored strategy. That's how they call it. This is a synchronous data parallel implementation of distributed deep learning. It's used to train on one machine with multi-GPU, so it's very similar to the PyTorch data parallel strategy, and in which case the model is replicated on all the workers in that single machine, and workers trained in lockstep. At the end of each batch, they do an all reduce on the gradient, and communication is done using NCCL for GPU by TensorFlow. And they have the TF distributed multi-worker mirrored strategy for multi-node, multi-GPU training. This is similar to the PyTorch distributed data parallel strategy. And in this case, they support multiple machines, each one with multiple GPUs. The models are also duplicated or replicated on the workers. And at the end of each batch, they do a ring all reduce to communicate the gradients. And what they also offer out of the box is this TF distributed experimental parameter server strategy, which implements an asynchronous training on multiple GPU machines, on multiple multi-node, multi-GPU machines. And automatically, TensorFlow assigns some nodes to be parameter servers, and the rest are workers that actually do the training. And a parameter server node is responsible for holding the model variables and receiving gradient updates for the workers and serving those model variables to the workers when they're done with their batches and ready to go to the next. This is a simple snippet of code showing how to use the mirrored strategy in TensorFlow. There's a lot of code examples out there. You can check it out. But just to show how easy it is, all you have to do really is to define or to create a strategy object. In this case, I picked the mirrored strategy, and then wrap the model definition and the model creation in the strategy scope like this. And there we go. From that point on, when you train on that model, it will allow you to train in parallel. So to wrap it up, it's a very easy to use library, very powerful with built-in support for distributed deep learning, supports both synchronous and asynchronous strategies, and has a parameter server implementation out of the box. It also has something we didn't have time to touch here, which is some support for cluster interaction via this cluster resolver package, which other solutions don't seem to have. Cons, I can't think of any con of TensorFlow compared to these libraries, at least to the ones we've seen before. It's very capable and very easy to use. There's a lot of resources out there. I didn't even scratch the surface here. Documentation, you can check out these links for documentation, tutorial, code examples, and classes, and so on. So the last deep learning tool that I would like to take a look at is RocketML's own homegrown distributed deep learning solution, RML-DNN. And what this is, it's actually part of a bigger stack of integrated cloud-based machine learning solutions that starts at the bottom with a cloud orchestrator component that interacts directly with the hardware and the cloud resources and cluster management systems like Slurm to allow a user to say, spin up a cluster, change cluster configuration, add machines, drain the cluster, all at the push of a few buttons through a nice graphical interface. And on top of that, then we have this HPC backend layer with the software accelerators. And these are high-performance C++ based applications for distributed machine learning in general. And RML-DNN sits at this layer. Then on top of that, we have an ML DevOps layer, which is a GUI-based platform as a data science workbench, on top of which then users can take advantage of popular applications, use PyTorch, use TensorFlow, open Jupyter notebooks and whatnot. And all these applications then interact down the stack with the high-performance computing machine learning tools and with the underlying hardware clusters and so on. Going back to RML-DNN, it is a data parallel synchronous DDL designed application, and it's cluster agnostic in the sense that it can run seamlessly on CPUs or GPUs, and it requires no user intervention to do so. You don't have to say, you don't have to add any code to send it from GPU to CPU and vice versa. It runs on both types of clusters equally. And it leverages these HPC, low-level HPC libraries like MKL, MPI for optimal performance. I'd like to take a look at this particular aspect of the RML-DNN design, which is this paradigm of parallelization as a first-class citizen. And what this is the idea that the application is designed from the get-go with distribution in mind. So there's no need for after-the-fact add-on code to be added and to be configured or written by anyone to orchestrate the distribution of data among workers or network operations among the workers. It's all done internally and automatically for you. And another consequence is the application can be launched exactly in the same way, either on a single machine, a single process, or on a large HPC cluster. There's no difference. And these diagrams illustrate a little bit of what I'm talking about. In a typical distributed deep learning solution, you'd have your serial script that you write. And if you want to launch that in parallel, you're pretty much launching replicas of that, and some glue code, some orchestration code is put in between. And this code is usually pretty thin, pretty easy to use, but you do have to add it, you have to configure, and in some cases more than others, you have to know about HPC and so on. And that's what this figure here represents. And on the right-hand side, it's kind of like what RML-DNN does. Every step of the way, like the loading of the data, the network setup, the training cycle, forward back propagation, all these things are done each step, taking advantage of parallelization and being aware, being rank aware of all the workers in the cluster and so on. So that's the difference in paradigm that I wanted to highlight. And the main two consequences of following this paradigm are, first, the user, like I said, is never responsible for any aspect of the distribution, initialization, setup, data splitting, communication, anything. And second, and very important, is the solution, that solution integrity is guaranteed by construction. What I mean by this is the solution will be exactly the same, no matter how many workers you run your code on. That's not always true in other systems, in other applications, and particularly in some of them, it's not true at all. And oftentimes it's the user responsibility to enforce that happens. And here it's guaranteed by construction. This is how one would go about using RML-DNN. It's through a very small code. It's the idea of minimalistic code. And I'm not going to spend too much time on this slide because there's going to be a demo right after where I show this in action, so I go over in more detail. But essentially, there's 4 lines of code here needed to run. A configuration line where you pass all the parameters configuring the run, set up this object of RML model class, configure it, and execute it. So more about this later. And last thing I wanted to show is a couple of results, in particular scaling results for RML-DNN running on both CPU and GPU clusters. On the left-hand side, this is the result of an experiment performed on the cloud using a cluster of CPU processors of type AMD. This is AMD EPYC 7742 processors. And we ran training of a 3D UNet network with 1.23 billion parameters. So it's a very large network on up to 128 processes, 64 nodes, 2 processes per node, to a total of 128 processes. And we got a speed up at that point of 109 times on 128 processes. So that's pretty good, pretty close to linear speed up. And another experiment where we ran on a cluster of NVIDIA GPUs of type Tesla V100. And these are machines with 8 GPUs per node. So we went up to 64 of those. So 64 times 8 GPUs, 512 GPUs, to train a 3D UNet model with fewer parameters, a smaller network in this case, 4.2 million parameters. And we reached a very good speed up of 482 times on 512 processes. Again, as these green lines show, pretty close to linear. So just shows the high performance and the very good scalability that RMLDNN is capable of offering. Okay, so now I'd like to show how one can easily use RocketML's deep learning solution, RMLDNN, to run a distributed deep learning training. And to do that, I'll go back to the platform here. And by the way, this platform that I'm using here is part of that vertically integrated stack of solutions that RocketML has. This is our data science workbench, if you will. And there's a whole host of capabilities and features here that I'm not going to go over. I wouldn't have time. But for example, one can easily launch applications on top of the infrastructure, notebooks and interpreters and whatnot, and data science applications. One can then run experiments that can be tracked. They go to this database and can be tracked here. One can deploy models and track their deployment and use them and share them. Finally, what's most relevant for my use case here, I can interact with the underlying hardware infrastructure by, say, spinning up a cluster, adding child nodes to a cluster, draining the cluster all at the push of a button. Say, for instance, if I want to add more nodes to my cluster, I can go here, pick the machine type that I want, and add, right? So I have already done that. I have a cluster up and running, and this console here is on the master node of that cluster. And as you can see, I have 2 nodes in the cluster, and here they are. I can run an NVIDIA SMI to show that they have 2 GPUs each. That's where I'm going to run my training. These are the 2 ones. And here on the master, all I have to do to use RocketML to run distributed deep learning is to write a script like this small, in which I load the RML model package and create this configuration dictionary of parameters configuring the run. In a more complicated realistic run, there would be more parameters. There's a whole lot of configuration that can be done here, but this is a simple use case where things like batch size, test batch size, the location of the MNIST files that I'm going to use for training, the loss function that I want to use, the optimizer and optimizer parameters, all these things. I'm going to run for 20 epochs because I want to show some things during the run. Actually, I can make it 10. That's enough. And some experiment name. And finally, I instantiate this RML model object and pass the network description file to it and some run directory name. And by the way, this network file is nothing but a Keras file describing the network. So it's the same format that Keras dumps and loads models or networks from. And then finally, I set up pass the configuration into this and call execute into this object, which then takes options for the hardware. Say, do I want to run on a cluster? How many nodes I want to use? How many processes per node, and so on. Okay, so that's all it takes. Let's give it a try. So now the first thing it does, it creates a run directory, right? And where all the log files and application logs will be written to. We can take a peek there. Say this is the main log of the application. We see that it's it's running, it's epoch 2, it does a cycle of training, and then does test and so on. So I'll come back here later, but now I'd like to show something cool as well that you can do, which is to attach TensorBoard to this. And when I do this, I have this port open 6006 where I can add an application. And now I have TensorBoard tracking my run at real time, right? So now I can plot things like the training loss, how it's going. Actually, that's test loss. Training loss is here. Yeah, how the loss is going down, how the test loss is going down, and how the test accuracy is going up, is going up, and update these as the run progresses. There we go. Okay, so everything looks like it's working. And here, back in the master, it completed, 100% complete. And just quickly, I'd like to go look again at this log, the application log, and see how it ran on 4 nodes, 2 machines, 2 GPUs each, using 2 devices on each machine. Set up the network. This is the network that we used, the optimizer, blah, blah, blah. Loaded the data set, and then it started running. It ran for 10 epochs, and at the end of each epoch, it ran test, and so on. So that's very simple, and that's how you use RocketML to run distributed deep learning.
Hello everyone, I'm Santi Advani from RocketML, and in this part of the tutorial, I'll cover best practices and gotchas to train large-scale computer vision models using distributed deep learning on HPC servers. So there are 3 main tenets of any high-performance computing software. The first one is for the software to work out of the box on CPU and GPU clusters. The second one is upper limits of Amdahl's law, which I'll cover in more detail now, and solution integrity. As you might have noticed in the previous part of the tutorial by Sergio, the distributed deep learning softwares from TensorFlow, PyTorch, PyTorch Lightning, Horovod, after making certain changes to your code, you can run them on a CPU and GPU clusters. And using RocketML, you can run the same software on a single GPU or a single CPU, and all the way to multi-node using a simple configuration. So the ability to run a software without any changes to the code and is an important tenet of HPC software. And that's what was covered in most of the tutorial done by Sergio. Upper limits of Amdahl's law is a concept, again, a key concept from high-performance computing. So let me explain the plot here and talk a little bit more about how it pertains to deep learning. So what I have here is basically a plot between the number of processors and the speed up. So on the x-axis, the number of processors can be number of GPUs, number of CPUs, or kind of any worker that we want to use for training. It can be TPUs for that matter. And it is in a log scale, right? So I have 1, 2, 4, 8. So it's a multiple of 2 on the x-axis here. And on the y-axis, I have speed up. That is, I'm looking at the ratio of time to solve a problem using n number of processors or workers divided by the time it takes to solve the problem using 1 processor. So the leftmost corner of this plot is basically starting with at a value of 1, 1. And as I increase the compute capacity, as I increase the number of workers, I'm computing the speed up. That is time to solve using number of workers divided by time to solve using 1 processor. So different lines here is basically based on different parallel portions of that software or that solve that problem. So for example, if there is very little parallel portion, that is the code or the algorithm in which that can be parallelized across multiple machines is very small, then the speedups will start plateauing after a certain number of workers. So for example, the blue line has 50% parallel portion, and it starts to plateau after a number of workers is equal to 16. And the dotted red line has a little more in terms of parallel portion, so there is more ability to parallelize the code. So it goes all the way to 56, and a little higher for this purple line, and a lot higher for the green line. So our goal is to achieve upper and upper limits of Amdahl's law. As you can see, if you can increase the number of workers and also get pretty good speed up, that means you're compressing your total time to solution without actually paying additional dollars to actually get the to run these workers, right? For example, if you can get a speed up of 4 with increasing the number of processors to be 4, your total compute time is still the same as spending one processor for 4 hours, right? Because your solution now is 4 times faster. So reaching upper limits of Amdahl's law gives you faster time to solution without spending additional dollars for getting the solution. So it kind of gets the best of both worlds. The last one is solution integrity. That is, even though you're solving the problem across multiple workers, you're using more processors, you don't want to give up on the accuracy, or you don't want to give up on the solution integrity. That is, solving the problem on 4 nodes or 4 workers should give you almost the same solution as solving the problem on 1, or solving the problem on 4 workers should give you almost the same solution as solving on 16. So you're not changing your problem as you increase the number of workers, and you're striving to get the same solution. Okay. So while we covered the CPU, GPU clusters aspect in the second part of this tutorial, in this best practices and gotchas, I'll cover the Amdahl's law and the solution integrity pieces in a little more detail. So as we have seen in the nuts and bolts tutorial that Sergio covered, this is how the training data parallel training is happening across multiple processors or GPUs. You have the training data, you split your mini batches, training data into multiple mini batches, and each mini batch is now split across multiple processors. For example, if you have a batch size of 32 and you have 8 GPUs, then each GPU or each P1, P2, P3 here gets 4 local mini batches, right? So each of them is only looking at 4 images. And they all propagate to the forward prop and back prop, compute the gradient, and there is a gradient reduction and loss reduction happening, and you're trying to update your weights across the board. So as you can see, the number of workers that you can use, the maximum number of workers you can use, is limited by the mini batch size. That is, say if you have 8 as your mini batch size, then you can only use 8 GPUs or 8 workers. Because beyond that, even if you have capacity, there isn't work to do, because the batch has exhausted the number of GPUs that we can use. So by design, the mini batch size gives you a limit on how many workers you can use, and beyond that you hit the limits, right? There is no speed up you can get even if you increase the number of processors, because the mini batch size is equal to the number of workers you can use. Okay. However, there is inefficient use of GPUs, right? Because let's say you have more GPUs and you want to solve your problem faster, it results in poor scaling because you're unable to use all the GPUs that you have. So how do you solve this problem? You have to increase your batch size. Simple as that. That is, instead of using 32, go for 64 or 128, or you basically say, I am going to use a bigger batch size so that each processor or each worker gets a bigger mini batch. That will increase your resource usage, and hopefully you should get faster time, faster solution back, right? But there is a model performance versus batch size conflict going on. That is, as you increase your mini batch size, there is a limit on to which you can go beyond a point where the convergence deteriorates. Right? That is, in the middle plot, what I'm showing is there is a green area where if the batch size is smaller than the certain value or greater than certain value, your performance starts to deteriorate. And this we actually can see in when we train models with larger batch sizes. So on the right-hand side, what I'm showing here is a loss reduction with respect to number of epochs for different batch sizes on a subset of ImageNet data using ResNet 50 and AdaGrad as optimizer. As you can see, when the batch size is 1024, there is loss decay, fine, good, decent loss decay. But as the batch size starts to increase, you see it takes longer and longer in terms of number of epochs to get to the same loss value. So there's this conflict, like, do you get more performance? For that, you need to increase batch size. But if you increase batch size, your convergence deteriorates. So in order to address this, you need to use large batch optimizers. That is, optimization methods that are suited for large batches. So there are kind of, at a high level, 3 types here. One is the first early work done by Facebook, which is learning rate warm-up. That is, as you increase, as you progress to your epochs, you change your learning rate. And by changing the learning rate with respect to number of epochs, turns out to be a good heuristic to train large batches. Okay, and that's work done around by Facebook around 2017, 2016 time. And this reference here can take you to that paper, and you can show that for large batches, you can use learning rate warm-up and solve problems faster using large number of GPUs. But it turns out that this method is unstable and there is quite a bit of room for divergence, right? That is, solution starts diverging and your loss never decays. So there are 2 methods that were introduced recently. They are called like layer-aware methods. One is called LARS and one is called LAMP. So the way these methods work is, instead of doing a weight update for all the layers using a single gradient, single learning rate, single momentum rates, instead you work layer by layer. So you take the weights for a given layer, you take the gradients for a given layer, and you update layer by layer and using the weights and gradients for that layer. So what turns out is, if you use layer-aware methods, then they turn out to work very well for large batches. And there are 2 variants that were proposed in literature. One is using momentum as base algorithm. That is, you use the vanilla momentum, but you just work layer by layer. And the other one is using Adam as your base algorithm. That is, you use Adam, but run Adam layer by layer. So LARS and LAMP have shown to work very well up to batches of 32,000 and without decay loss in any generalization of the networks. And beyond batches 30K, it still seems to be an open problem. And LARS and LAMP are first order methods that you can use to go for large batch optimization. The other category is Hessian based methods, right? That is, if you go beyond gradients, you can use Hessians. Hessians is basically second derivative of your objective function. And Hessians work kind of very similar to your layer-aware methods, because instead of working layer by layer, you're working with your eigenvalues and eigenvectors of your entire Hessian matrix. And they in turn have very similar effect compared to Lars and Lamb, and gives you better convergence probabilities for large batches. Okay, so large batches are important when you're using distributed deep learning on HPC servers, because you can use more capacity, but you also need to update your optimization method so that you don't suffer with convergence problems. Okay, so if you take care of all these aspects, then you can reach upper limits of Amdahl's law to solve large-scale deep learning problems on HPC servers. The other aspect is solution integrity. This is the third tenet that we were talking about. And the data sampling aspect affects your solution integrity. So here, what I'm showing is on the left-hand side, I have Horovod, and on the right-hand side, I have our implementation of distributed deep learning, which is RML. And on the left-hand side, each worker reads a random portion of data. Let's say I have 1024 to be my global batch size, and I'm using 256 CPUs. Each CPU is picking up four samples from the entire pool. And they pick random, like 4 random images. That's the implementation in Horovod. So as you increase your batch size, okay, as you increase the batch size from 1,000 to 2,000 to all the way to 16K, when you're randomly picking samples from your pool, there is a higher probability of data duplication. That is, 2 workers are mostly seeing the same kind of data. Okay, this in turn results in deterioration, because you're seeing same samples, there isn't a lot of randomization, and your gradients turn out to be inaccurate, and that will result in loss in conversions, right? So as you see in Horovod, because the data sampling and data sampling is not done accurately, as for larger batches, you see a deterioration in terms of convergence. But if you make sure that each worker is reading a specific portion and there is no data duplication, the convergence deterioration is minimal, and it doesn't exist in our implementation, and you can go to really large batches without suffering on the solution integrity, right? So here we were able to go all the way to 16,000 global mini batch, and we have not seen decay in terms of our convergence when we made sure there is no data duplication. Okay, so data sampling is an important aspect to take care of when you're working around HPC servers for deep learning training. The other aspect is batch norm. So batch norm improves training speeds. Right? It enables larger learning rates, and it makes your training less sensitive to weight initialization. And the way batch norm works is the input data is normalized to 0 mean and unit variance, and you have 2 learnable parameters, right? So that's is basically a new component introduced for deep learning training, and has significant impact in training deep learning networks. But batch norm also introduces the problem with that the input data is different for different workers. So the mean and the variance are diverging layer by layer as you do your forward propagation and back propagation. So for tasks like image classification and object detection, when the local mini batches are large, right? That is, your global mini batch is, say, 256, and you have 8 GPUs. So each worker gets 32 local mini batch. So in those cases, the mini batch sizes are reasonably large. So the mean and variance across multiple workers is not way too off. They are in the similar distribution, and they need not be desynchronized, right? So you need not synchronize these batch norm related variables. There is zero mean and unit variance, and synchronization will slow down training because you need to communicate across all layers where you have batch norm. So for tasks where local mini batch sizes are large, you can just do unsynchronized batch norm and your solution should be fine. But for some tasks like semantic segmentation, right, where local mini batches can be too small because of large memory limitations. So because when you're running a segmentation task, and especially when you're running UNets or any of these fully convolutional networks, the memory footprint requirements are large. So on a single GPU, you may only be able to fit small mini batches. And in that case, the divergence between two workers in terms of mean and variance can be large. So synchronization is something you need to do. That is, synchronization of mean and variance becomes important. Otherwise, your overall convergence and solution suffers. So this paper by Zhang et al. And others on context encoding for semantic segmentation in 2018 CVPR covers this aspect of batch norm and where you need to use unsynchronized, where you use synchronized, and the underlying math of how to do it is covered. And I definitely recommend anyone doing advanced distributed deep learning to go look at that paper. To summarize, in this part, we covered the key tenets of HPC software and in specific upper limits of Amdahl's law, how to reach that. Whereas higher throughput is not faster time to solution, and you need large batch optimization methods to make use of large clusters. And solution integrity wise, avoid data duplication for large batch training, and use unsynchronized batch norm for moderate local batches, and use synchronized batch norm for small local batches. With that, we conclude the first block of this tutorial, going through all the nuts and bolts of distributed deep learning. And in the next part, we'll cover various different applications by our collaborators from Iowa State University and Shell, and they'll talk about how to apply these for different use cases that they're working on. Okay. So thanks for your attention, and I look forward to answering any questions that you may have.